Welcome to Module 2. So in this module, we'll talk about the Python setup, notebooks, virtual environment, and conda. So here, when you have these slides, you can click through these tables of contents. Generally, I think this is a first-year class, and I can't take it for granted that you all are masters of Python yet. So we'll basically just set up the environment and get some fundamentals down initially. So at the end of this module, you ought to be able to explain and even compare different virtual environments. VEnv, a virtual env, maybe conda environments. You'll be able to configure Jupyter so that the correct kernel or interpreter is used. We'll define what these mean in a moment. You'll be able to create a project environment, run a notebook containing code, and produce a nice plot in a table. And you'll be able to export your environment for reproducibility and justify your choices. I think it's important to spend a few moments on this at the beginning of the course. A little bit of setup now will save you a ton of time later on, right? So it's going to be the case that your environment might break halfway through an assignment or halfway through a task. And this is just going to cause you to lose momentum, lose time, lose focus even. Python can be a little bit temperamental when it comes to the versions of the modules or the libraries that it's using. So, take a little bit of extra time and try to solve problems as soon as possible, early. Set up your environment in a way that makes sense for you in order to be maximally productive in the future. So just a kind of a rule of thumb, if something feels kind of annoying but minor now during your setup, it could become huge and painful later, almost certainly late at night when you're right in front of a deadline, in which case you don't want to be dealing with these annoying and small challenges. Or even if they remain annoying and small, but they're pervasive and they keep on occurring over the semester, in aggregate, it's going to cost you a lot of headache, so might as well solve problems early. So in this module, like I mentioned a moment ago, you're going to be able to reliably run notebooks, import packages, and also just know which version of Python is actually running your code, because you can have multiple versions of Python and its libraries on your computer at the same time. So this course is going to be very Python-centric. It is almost certainly the most popular language for data science. It's hard to get statistics on this. Occasionally other languages, which I'll mention in a few moments, kind of are also apparently very common in aggregate. But as computer scientists, we tend to use Python. There are a very rich collection of modules or libraries that we can use and have at our disposal. So NumPy, Pandas, Matplotlib, scikit-learn. I mentioned these in a previous module. We'll come back to them soon enough. There's a massive ecosystem, so lots of tools for data wrangling, machine learning, visualization. There's a really great community. There's all kinds of documentations out there and tutorials. So to learn a language and to become familiar with it, there's lots of supports. It pairs well with Jupyter notebooks and VS Code workflows. So if you're already using VS Code, you're probably not using Jupyter unless you're using Python, although you could. But it just works well in those environments. We'll discuss these in a few moments. I'm going to mention a few caveats right now. This might not make too much sense at the moment, but Python, unlike the one true language, C or C++, allows you to type variables dynamically. So the same variable name can start as its life as an integer and then transform into a string and something else afterwards in Python, right? Which can be very handy and very useful in some situations, but in some situations, if you don't know what type a particular variable is, that can cause challenges, so it's good just to have some tests available. It's good to have typed loops, so Python has been getting more and more effective and efficient over the years, but it still pales in comparison to C and C++, but there are various approaches to improving things. I welcome you to click on this link on vectorization. It's just sort of like a software coding hack, or technique rather, that can help you improve things. And be sure that you're using the right environments. That's a large part of what today is going to be about, is pinning environments appropriately. Other popular languages in data science include R. Lots of excellent statistical modeling. This is a slight typo under Canadian spelling. Should be two L's, but whatever. R allows you to do visualization. There's all kinds of ways of tidying up your code. There's a good academic ecosystem, so a lot of our colleagues in faculties and departments outside of computer science use R. I literally am working on a project now from another group outside of computer science at Dalhousie who use R. It can be good for exploratory stats. It can be good for producing bespoke plots, so R has its place. Click here and here to learn more about R itself and a studio desktop to code in R respectively. SAS is popular in enterprise analytics, so if you go into data teams at a large, typically large organization, you're more and more likely to encounter SAS. It's used within regulatory contexts, especially things like pharma. There are stable procedures, there's cloud options. If you are an academic like myself, there's SAS on demand for academics. Click on this, learn more about it. This is just kind of for your own knowledge, because eventually as you go out into the world, you're going to encounter people who use R, people who use SAS, and it's good at least to understand a little bit about what they are and how they differ and what their strengths and weaknesses are. The good news is, like in so much in computer science, we have lots of tools at our disposal, and some of those tools allow us to do interoperability correctly. So you can kind of mix and match R and Python. The project I mentioned a moment ago, actually, like it started its life as R, and now it's transforming to Python. And often, the data itself is in some format that we can share. We can, interoperate. So, like, we can start doing some analysis in R, for example, or in SAS, generate some temporary intermediate results in CSV or some other formats, and then bring those into Python to continue its life. So, Python in virtual environments. So this is not a coding class, so we're not going to talk too much about, what is a for loop and whether you should indent with tabs or spaces or any other controversies of that type. We just want to make sure we have our tools set up in a way that's usable. So, do you already have Python? The chances are you might. Specifically, do you have version 3? I mean, we've been using version 3 for years and years and years. Probably you're going to want to use something like version 3.14. Version 3.9, I think, is becoming obsolete now. Regardless, if you're on Windows, you can open up PowerShell or some other command line utility and run pyv or python-v or where Python to see if it exists. In Mac OS, which is sort of a mimic of Linux, you can use Python 3 version or which Python to do the same thing. If you have Python, but for some reason you don't know what specific version you're doing, here, copy some code, copy it into your Python environment. This imports the sys library and the platform library. It uses these to print out the particular version you're using, and you should see 3 point something or something as an actual number. So if you see something like this inside your path, then you're good to go for now. If you don't, then there's various ways you want to install Python if you're in Windows, Mac, or Linux. I'm not going to go through this right now, but again, go to these slides on the course website, click on the OS that you're using, and then, there's only one allowed version of Mac OS at a time, really. Linux comes in various flavors, which is both its strength and its challenge. So, figure out if you're using Ubuntu or Fedora or one of their subtypes. I've linked to notes on all of these. If you use Arch, by the way, you can use Pacman. We're going to use conda as much as possible. So, like in my environment I have right now, I have different, use cases I have. One of them is this course, and I want to use one set of libraries for this course and maybe a different set of libraries for research I do in real life. So I like to have different environments with different sets of libraries with different versions installed in each of these separate environments. One of the best ways to do this is using conda. So I've suggested a way to set up your environment, and you can learn more about it at this link. So if you already have conda installed, you can create a new environment. You can name it something that's relevant for this class. You can name it 1109. You can specify the version. I specify here 3.11, but I think I'm using 3.14 on my desktop. So now you have an environment. You can see which environments exist in your computer by saying conda env list, 3 words, and that will list you the environments, and you can switch to the appropriate environment using activate. Okay, so we're gonna explore this together in person. I just want to kind of highlight this as a pointer for now. So this isn't just to avoid pains, but it's also part of the software engineering process. Okay, so one pain you want to avoid is just like constantly not having the libraries installed or having mismatches or conflicts emerge in your system, which are hugely problematic and a waste of time. So conda helps to make things clean. But also when you ship your product, you want to make sure that it will work on someone else's machine. So you don't want to be in a situation where you submit work and then whoever's running your work says it doesn't run, and you don't want to say, well, it works on my machine, because that often is not believable to many people. So graders, teammates, customers, decision makers, if they install slightly different builds, the behavior will change or break, and we don't want that to happen. Okay, so we want to be able to package with installable artifacts. I click on wheels, so check this out as an example, which we might come back to in this class. But just make sure that others are getting the same code, and if you're compiling bits, make sure that they're contained as much as possible. You want to be able to avoid cross-project collisions. Again, you might be shipping your product, even from this class, with a particular version of the pandas library. Somebody else might have a different version on their computer for research. So maybe they're using some obscure library which depends on an older version of pandas, so they have an environment in which they have an older version of pandas. You don't want them to run something that you assume has a new version of pandas, and there's some mismatch. Doesn't work, there's problems. So per project environments, having one environment per project can seem like overkill, but it can be hugely helpful, and it's quite manageable in my experience. So many other data science tools also rely on other tools outside of Python. Sometimes we can package them in various ways, but spoiler alert, even if these packages are outside of Python, we can still, from which we've developed an environment on a previous slide, we can still package external data science tools or other tools using conda. We have 2 kinds of tools for 2 kinds of subtly different jobs. So packaging basically helps us answer the question, well, how does someone else install what we've built? So this basically is shipping a distribution. We can prefer wheels, which I mentioned earlier. So installation is going to be fast. So if you're deploying something, it's fast, reliable, it's compatible across operating systems, as long as they use the same components. Publishing flows, like everything's straightforward. We also want to be able to have environments where it will run without breaking other projects, right? So we don't want, for example, for you to need to install particular versions of libraries that break other things that someone else is working on in their system, right? We want to isolate so that we're not breaking other people's stuff. So we want to freeze what we run. We want to isolate how we run it or where we run it, like in an environment. And we want to make things as reproducible, reviewable, and shippable as possible. So virtual environments is also something called VN. You might have learned about in other Python classes. So you can create these directly from Python. So python-m venv.venv will create a virtual environment. It's created in different places depending if you're in Windows or Linux, or Linux and Mac clothing. You can install. Well, when you're in the appropriate environment, you can install libraries using pip. Either you can call Python using the module pip and in the function install, and you can ask to upgrade pip, or you can run just pip by itself on the command line. Sometimes it's pip3, like maybe pip doesn't point to pip3 for some reason. but usually you can use pip3 if in doubt. So this environment will create a requirements file, which we can use for shipping. There's a tutorial here and a guide over here. Click on these. This is and read them. There might be some tasks we want to do in class related to these. So I personally prefer conda to venv because it's more functional. It can do more. So it manages packages, manages environments in various languages. Could support binary builds. So here we've seen this kind of already. So here we created an environment. We use Python 3.11. We start off by bringing in pandas and matplotlib, but we can add new libraries to our environment that we've already activated as we go. So here we've created the environment. Here we've activated the environment. So now we're like in environment 1109 module 2. I don't run a different environment for every module in this course, but just for the sake of the story. If you want to ship, the environment, then you'd use conda environment export, and then you'd export it to this YAML file, which have information about your setup. There are different channels you can use in conda. Click on here to learn about them. Many projects, and myself included, like I'm not a project, I also enjoy conda forage. It's consistent, lots of people use it, there's lots of support, lots of breadth. So you can set things up for conda forage, usually that's by default when you install conda. And you can run pip inside conda. So once you've already activated your environment, you can go back and do pip install whatever library you find you need. It installs into that environment, and then you have it for your interesting data science work. There's some additional guidance for how to do pip inside conda here and here. Again, I don't want to go into too much depth. It's a bit outside of the scope of this tight module, but it's important for you to click on all of these links and learn about how to install conda, how to install modules with pip inside of conda, and so on. Just a couple of gotchas just to highlight them, because you're probably going to encounter some of these. After you run an initialization of conda, conda can auto-activate its base environment, like its initial default environment, whenever you open a new shell. This happened to me this morning. I opened up a new shell. I tried to run something. It told me I don't have the appropriate tools. And then I did conda env list, and I discovered that I was in the base, so I had to switch or activate into the appropriate environment. So that is perfectly fine. It just means you have to make sure that you're switching to the appropriate environment. But what this can sometimes trip you up is if you forget that you should be working in a particular environment, you open up a new shell, you start using pip to install all kinds of libraries. They'll be installing libraries into whatever the current environment is. It could be the base. And that means that you might be overwriting things that you previously assumed were in base, and that's a problem, because now you're messing with an environment that's being used for a different purpose. And also it means that you're not actually updating the environment you think you're updating, which means that you're going to have to go through this whole thing later. So if you do this, you could you could potentially break. You think you're working on project A for this course, you're installing in another one, therefore you're breaking some other project. There's versioning collisions of all kinds that, maybe one environment you're installing assumes one version of a library you install assumes a particular version of another library, and that is inconsistent with the environment you're in. And all these kinds of problems. So there's ways around it. You could stop activating the base on every new install with this command. You can again, we've already talked about creating project-specific environments. You can always do conva info envs. I use conva env list myself, but it's the same idea. And then keep on checking what version of Python, which version of pip you're using, as much as possible. A little bit of checking initially will save you a lot of trouble later. So just want to highlight the differences between venv and conda. Venv is really like a typically a per project Python environment, whereas conda is that and so much more. It's a much more global environment and package manager. You use pip or conda on the command line respectively, but you can run pip inside of conda. venv only works with Python. Conda is much more general. Binaries, you can use wheels within venv, but how this actually is deployable can depend on your tool chain, what operating system you're using. Conda, Forge, and all kinds of other binaries are really helpful with Conda. You produce descriptions of your environment in both of these. venv produces a text file, which is fine. Conda produces a YAML file. venv sometimes can be used for pure Python stacks, lightweight apps. I find that Conda can be fairly lightweight also. I haven't found it to be too onerous. But when we're doing data science and we have a lot of dependencies and a lot of tools that we're applying to a problem at once, especially the machine learning tools, Conda might be more appropriate. venv is minimal. I say ubiquitous. It's not really ubiquitous. Conda, fewer headaches in my experience. Generally, things to watch out for venv is native builds for different operating systems. Things for Conda, just like for venv actually, is making sure you're not mixing channels. It's a slightly larger footprint, but for most deployments that won't matter. So generally, like the rule of thumb here could be that if you're just doing pure Python, you might prefer venv, but even if I'm just doing Python myself, Conda is my flavor of choice. So there's two common routes. You can choose one or the other. I again highly recommend Conda. Click on Miniforge, click on Anaconda, run them both. We've described this already, but not to be too redundant, but follow this path according to your preferences. Okay, so development environment. So we have the virtual environment, or an environment in which we have libraries and our tool versioning sort of sorted. But that isn't really the same thing as having a development environment in which we're actually coding and getting partial results and checking on our progress and so on. For that, we need a development environment. So I want to differentiate what a source file is from what a notebook is. So data science, like we talked about in a previous module, is not really just a straight line of like we develop something and then we debug it after that, and then after we've sufficiently debugged, we're finished. There's going to be an awful lot of exploring and kind of qualitative analysis and experiments. I say test here, but this would really be validate according to the vocabulary we established in a previous module. Keep on fixing and fixing and fixing, explaining, maybe refactoring. It's going to be a complex, looping path we take. So a notebook will have code in it. So a notebook incorporates code, and you can actively do your coding in it. But unlike just software development environment, you'll also have output. So you'll generate graphs, you'll generate partial outputs, you'll have temporary variables that you'll have pop up, and then you can use for reasoning, and you could iterate on small parts of it without having to rerun the whole software stack over and over again. So analysis is transparent, it's quick, it's replayable, it's fun. This kind of replaces having the 3-window problem. When I was a student myself, I had Emacs, again, my preferred editor, and then I had a terminal to run things, and then I had notes and script and so on. A bit of a mess. This kind of brings it all under one roof, so to speak. So you could run, inspect, narrate. You can take notes, like just mark down notes inline. So it's like a lab bench where you're actually doing the experiments and you're keeping a record of your experiments. But it's also a notebook, so you'll be able to open up little sections where you could just comment things to yourself, and even eventually, as we'll see later in this course, prepare beautiful notebooks that you could share, and like the notebook itself becomes something that you deploy. So yeah, when you share it, a notebook is sort of like an executable paper, like a research paper. Others will be able to rerun your steps, see the evidence. It's not exactly a shippable product, but sometimes it serves that same purpose. So a notebook is normally formed, in our context especially, takes the form of a IPYNB notebook. So PY, Python, NB notebook, and so on. It's essentially a JSON document in which you have a lot of cells which are ordered, like one after the other. These cells are this weird-looking symbol, which some of you might think is the Earth symbol, is actually the exclusive OR symbol. So a cell can be either markdown, where you're just doing text and you're doing bulleted lists and all that nice markdown stuff, or exclusive OR, it's code. These cells can also be associated with outputs. So when you run code, it produces outputs. And then there's some extra metadata behind the scenes, which you can see if you open up the raw JSON file. There's basically two modes. So each cell you can open up in edit mode, where you're editing the content, you're editing the code, you're editing your markdown, or you kind of run it. When you run markdown, it produces the beautiful looking markdown, document, or pseudo semi-document. And when you run code, it runs the Python code, and then it generates the outputs afterwards. So here's kind of what it looks like. This is me running a Jupyter notebook, or a notebook. I'll get to Jupyter in a second, but a notebook in my environment. So you can see this is a cell over here. So far, nothing's in it. You could add a cell above. Can you see my? You can kind of see. You can see my pointer. So, sorry, I'll move this way. You can see you can add cells above using this button. Add cells below using that button. You can delete a cell with this button. You'll play around with it and you'll become familiar with it. If I were to start typing here in my environment, it would mean that I'm doing code. Because you can see here, this is code. If I wanted to switch this to Markdown, I'd click down here. I'd select Markdown, and there we have it. We're going to do all this live in class soon enough. Here's how you run a cell. You just click this button. This is like the play button. So you play there. It's a stop button. So here we've written some code. Here the code is simply as print hello 1109. And then if you run this, either I think using Control-Enter in Linux or whatever you're using, it's some other combination. I think it's Command-Enter in Mac. Try it yourself. It produces the output. Here it's hello 1109. Now I've created another cell here. This cell is also code. This code imports the library, the time library, and then I have a bit of code that just calls that library and tells it to sleep, and then the argument is for 5 seconds. So when you run this, you can just test it out yourself. You'll notice over here that these cells have these sort of grayed out indices over here. So here's index 1. This is the first cell. This kind of highlighted area means this is the cell I'm actively editing or running, and this star over here means that it's actively being run currently. Anyway, we have another module down here. This is, now we're defining a function. This function is called say hello. It takes one argument, which is recipient, and all it does is return the string hello, comma, something, and the something is going to be whatever I pass in as recipient. And then I'm actually going to call this function down here, say hello, and then what I pass to the recipient is the world. I'm going to send this to the whole world. When I run this, I define the function, and then I run it, and then it produces hello, and then the argument is passed in, and it's the world. Right? So pretty straightforward. Here you can see there's no star. Even though this is highlighted, and this is the cell I'm actively editing or running, it's already run, so the star is now turned into the number 4. So there are some shortcuts. Like any good tool, you're going to have keyboard shortcuts. It might be a little bit different based on what tool you're using, so don't take my word for this exactly, but usually A and B helps insert cells above and below, as you might guess, from the characters themselves. You can switch a cell to Markdown or to code with M or Y. You can delete a cell. You can run a cell with Shift-Enter, and then move down. Your Control or Command-Enter, like I mentioned a moment ago, is running in place. But it's always better to learn through practice, so just get comfortable with the tool yourself. So I mentioned Jupyter before, so we're getting down to define what Jupyter actually is. So we have a notebook, which is our JSON file, which is in a file format IPYNB. So this is where we're kind of editing it somehow, and I'll talk about how soon enough, but when we actually run these cells, it'll send the code to a kernel, which is a particular Python environment running in like conda or VNV potentially, like we mentioned earlier. And this environment will have packages, so a particular version of pandas, a particular version of NumPy. It'll include files and data, so maybe a comma-separated file, like a CSV file, comma-separated values, maybe even images or other data, and it'll also incorporate outputs in it. Okay? If you have an environment set up with the wrong kernel, then your code might not run. Like your code in your notebook might assume a particular library, which is packaged in a different environment than the one you're currently running. So again, be aware of that. you're likely to encounter this several times, a module not found error. So you've already done the pip install of a library, but you've accidentally installed that in a different kernel. So just make sure that you're running the appropriate environment, the appropriate quote kernel. It's connected to your notebook. You can, I say always, but you can generally verify which kernel you're running with sys executable. I think we've already given you an example of that, just to make sure you know which Python is running. Sometimes that's not enough. Like you need to know, like, not only which Python, but which library is running. Here's some code I've actually run myself. So the environment that I'm using to produce these slides actually has a Python kernel behind the scenes, and I have a conda environment that has its own, Python version and everything. So when I run here, like this is the code that I'm actually running to produce this output in these slides. So I say, import sys, print the executable version where it is, and print the Python version. I think I mentioned earlier that I'm using 3.14, so there it is. This, I think, I'm not giving you too much information about my environment. I'm using a particular version of Linux where I have a home environment, and my folder is called Frank. So I don't think I'm giving up any private information there. It's fine. You can scroll down here. If you haven't noticed already, you can interact with these slides by scrolling down. Here, I'm also importing pandas. I'm calling pandas PD now. I'm also importing matplotlib, and I'm printing the versions of pandas and matplotlib using these commands. So now I also know what versions they're running. So feel free to do this yourself in your code. So again, we live in a free society. Thank goodness we live in Canada. In a free society, we have real choices, and likewise, we have a choice of what development environment we have to use. Jupyter Lab is by far the most common, and we're generally going to assume that we're using that in this course. But VS Code, I've noticed a lot of students like using VS Code, so that's perfectly fine. Jupyter Notebooks run there as well. We'll talk about Google Colab in a moment, which is an online platform, and then Emacs. I love Emacs, but even I use Jupyter Lab for my notebooks, but we'll talk about Emacs too, because everyone should learn more about Emacs. Installing Jupyter is very easy. So there's a website, click on it, here it is. You click on install, it tells you how to install it in your environment. So you should be good to go fairly easily. Let's go back to the slides for a moment. And everything's good, looks good. So click there, and it'll give you instructions, but basically you'll get something like pip install Jupyter Lab. Some of you might be using a platform that uses Brew. I think Mac OS uses Brew a lot. It's called Homebrew. Some versions of Linux prefer Brew. You set it up to use the Conda Forge channel. Again, click on the links, and if you have problems, we can discuss it. But super easy to install. Normally, it's as simple as a 3-word command. And then you run it from the command line using Jupyter Lab. So just in practice, knowing what runs when, or what runs where. When you launch Jupyter Lab using this command, it will actually start a local server on your machine. It'll run it on localhost. It'll open up a port. The port might not always be 8888, but I think by default it often is. And then it'll also open up your browser of choice, and create sort of a user interface in which you can interact with your notebook. I showed you a screenshot of my notebook earlier. So the browser, your web browser, is basically the interface in which you interact with your file. The kernel is a process that's running behind the scenes, ideally in a conda environment that runs your actual code. And again, same thing happens for me when I'm producing these slides, although I'm producing these slides in Emacs. When you close the server, this also shuts down its kernel. Sometimes you have to do an extra step of explicitly confirming that closing down, but generally that's how it works behind the scenes. So Jupyter in practice, but just for completeness' sake, let's walk through a few. So VS Code, click there. You can see how to download it for Linux. Again, as you probably get by now, I'm in Linux right now, so if I was in Debian or Ubuntu, I might use Deb. If I'm in Red Hat or one of its variants, Fedora, I'd use this. So this is very similar. There's an interpreter selection. This interpreter selection drives the kernel selection. There's instructions here on how to select the proper Python interpreter. Very similar to Jupyter Lab. There's a front end, there's a server, there's language kernels, and you can click here to learn more about the back end of VS Code. In VS Code, you should also verify your editor, verify your kernel. The same basic code you can copy here and run it, and just to confirm your versions of Python and say pandas or whatever other library you have. Google Colab. I think I should have made this this slide scrollable, so I will fix that before I post this. Google Colab can be useful in some situations where you need access to GPUs, like you're doing heavy-duty machine learning. Maybe you have a laptop that you're not comfortable doing heavy-duty machine learning with. You might not have any other access to GPUs, so Google Colab is a quick and dirty way, and free, at least by default, way to deploy Jupyter notebooks and run things in the cloud. So it's fairly easy. Up here, I'm not sure if you can see, but there's a little connect button where you connect to GPU or even TPU resources. You upload your Jupyter notebooks to Google Drive, and then you access that Google Drive through Google Colab. It's all online. I mean, this presumes that you're comfortable putting things on Google. It can be useful for little demos. It can be useful for getting assignments sort of up and running. There are limitations, so Google Colab can remove access to the GPUs. Like, you can't just run them indefinitely. Usually they're time-based. So sessions time out. Storage is ephemeral, so sometimes whatever you end up storing, partial results are also, they evaporate, so just be aware of this. So Google Colab, good for trying code, but I would not recommend it for shipping projects. Always export your, can I move myself? Yes, I can. Oops, that's not who I wanted to move. Again, how can I move my, there I am. I'll run over here for a sec. So you can always export your notebooks, again, produce things locally as much as you could, encapsulate your environment specifications, and make it deployable locally if possible. Here's a link to Google Colab. So click on this, you'll see the environment. Generally, it works well. So if in case it's not clear already, I love Emacs. It's not for everybody. There's a kind of a very adamant debate that goes back from before my time about Vim or VI versus Emacs. And I think most people these days still prefer Vim, but it is what it is. So here's an example. You could run Jupyter, like Emacs, sometimes it's called like the best desktop environment. It happens to have a text editor in it, but in theory it's a text editor. Here you can kind of see, here's Jupyter Emacs Universe. You can click on this. Well, here, I'll click on it now for you. It kind of walks you through features of running Jupyter notebooks from inside Emacs. There's a Melpa package. Melpa is how you get packages in Emacs to do all kinds of things. But Emacs, if you're not already comfortable with the key presses, or kind of Emacs has a particular way of doing things, and if you're not already familiar with that, I'd say, put this, keep this for later. We've kind of already talked about this. I'll move myself aside. I'll move myself off screen for a bit, actually, over here. So the project folder is where you have your assignment, your code, it's your home base. That's where your code, notebooks, files live. You have an environment, say with conda, defined by a YAML file or a requirements file produced from pip. Then you have the actual environment, which has Python actually running. This is where packages are installed. It's just local, not global. This will produce a kernel specification. It'll have particular versions of tools that you use to install of libraries in this environment. You can also have Python scripts, so you don't need to just use the environment to run Jupyter notebooks in Jupyter or VS Code or Emacs. You can also use your environment to run scripts on the command line. And in all these cases, you're going to be producing artifacts like figures, tables, new code, etc. From it. So it's a powerful tool chain, very generalizable, lots of specific ways you can get into the nitty-gritty, which we're not going to get into immediately, but in the course you'll become masters of this tool chain. So just a few examples. So we start with like raw data. We're going to clean it up a little bit, compute some features, visualize, make some claims, and then see if it's aligned with decision-making processes. So later on in the class, we're going to talk a little bit more about more impactful use cases than coffee. Although coffee is very important to many of us, so maybe this is, in line with the cancer version we saw in the previous module. But anyway, this is the example I came up with. So we may have a question, a scientific question. How does the temperature outside relate to people buying hot drink orders per day? Maybe you have a vague idea that people will buy more hot drinks on cold days and more cold drinks on hot days. Okay, so that's our kind of question. We want to break it down into measurements or metrics. This will include units like temperature, and obviously we'll use metric, and orders. So the count of orders per day will be our metric we care about. So as always, well, almost always, here's some code provided to you that will help you run it yourself. I'm going to maybe talk about this later, but sometimes I might include errors in my slides or in my code that ideally some of you will pick up on, and then you'll bring it to me in our in-class meetings, and then you might even get some extra participation marks for detecting problems. So this isn't just, for the sake of giving you the code. I want you to run this code and make sure you're able to regenerate what I'm producing. Anyway, so there's a lot going on here. Well, not a lot. There's a fair amount going on. I'm defining a comma-separated file over here. These day, temperature, and Celsius, and orders are my headings, and then down here is my actual variables, or the values in my variables. This is a CSV, so I can use read CSV to read the CSV into something called a data frame, which is from pandas, which I'm calling PD for now. So PD pandas read CSV. And I can take the orders that I have in that data frame. I can divide by the maximum number of orders I have. So this is like calling max on this will give me the maximum. This will give me like a normalized or norm of the orders. So I'm just kind of like setting everything is relative to the max. And I print it. I print a full data frame, which is this. So this is just this is just the result that I've actually my Python produced in the slide. And then I'm going to produce a little figure here. Oops, sorry. So this figure is has a particular size. It's going to be a scatter of the temperatures against orders. What S for a moment. S is just a visualization parameter. I have a title. I have labels. Always label your x-axis, always label your y-axis. I'm going to produce a typed layout. You don't have to do this, but it can be helpful, and then I'll just show it. So this is what my Python environment has produced. So here's all the data I have. So let's just make sure what's going on here. So I have one instance where the temperature is 3, and I have 210 orders. So down here I have temperature of 3, and this is 210 orders. So that's the first data point. Is this trend linear? It looks like all these points kind of fall in a line. We'll come back to what that means, what linear really means later. What other variables might be a confound here, right? So here all of my data is just like a weekday, and the temperature. But what if weekday actually plays a role? Maybe people are more interested in buying a coffee on Monday morning than they are on Wednesday morning. I don't know. Temperature doesn't tell you the whole story. What if it's raining? What if it's snowing? What if there are particular promotions going on? What if the promotions are only on hot drinks? That surely will affect the number of hot drinks that are being ordered, right? So, we want to use this information for some real-world decision. In this real-world decision, we want to know how much, coffee grinds to stock, So we don't want to have too much. We don't want to have too little, because that can affect our costs and our profits. How many people do we want to have on hand at our little coffee shop for chilly versus warm days? This can help us make decisions for our coffee shop. So it isn't just a matter of plotting dots. You can see how even in this example, we have real world decisions that will affect our profit and costs and the livelihoods of the people who work with us. So we can measure visits per day. There's some noise in these measurements, and this can mask the truth. So I've made this highlight here. The truth is what we're after always. So there's a signal in the noise, and the signal is close to the truth, so we're looking for it. Always remember that. So we want to simulate 2 weeks of daily site visits and use a kind of a 3-day window around it. So again, our units are going to be counts per day. Here's the code to generate this new graph. This one will produce averages, rolling averages, given these function calls. They'll have a window of 3 data points each, and we'll have the sender set to true. We'll have a mean. We'll talk about what that means later. We'll have a standard deviation also. So this is the average, and then the kind of a range, speaking loosely. And then we'll use those in our new graph. So kind of like trying to filter out some of the noise that can occur in these drastic fluctuations and get the actual smoothed trends according to means. Now we have this kind of orange dotted line over here, which is, as you can see in the code yourself, is our means. And you can see there's an upwards trend, but the upwards trend is not as wildly variant as the raw data points. So we've gone from raw data points to something a bit more refined. And then we have this sort of range, this kind of light blue range around our data is defined by our standard deviation or sigma over here. I know that a lot of you probably think sigma means something else, but let's stick to sigma meaning standard deviation. So we have some takeaways now. We have a smoothed trend. The smooth trend is maybe closer to the ground truth, but it's not exactly the ground truth. It even depends what you mean by ground truth. So it's not the ground truth in the sense that it's not our raw measured data. It's a more abstract representation of the truth, but it's still abstract. It might help us to start forming an intervention, but we might need more data too. So the same code might run differently if you run it out of order. So this goes back to the idea of Jupyter notebooks, and you have different cells. If you run one cell at a particular time, and then run another cell, and then go back to the first cell, sometimes the state of your kernel might be something that you might not actually recognize. So here's one cell, call it cell A. We'll define X as being 10, we'll print it, there it is. And now we'll define in another cell, this is the second cell, we'll define Y as X plus 5. And then we'll print out Y. So I want you, in your Jupyter notebook, which you've already set up, I want you now to delete cell A and then to run cell B. So do you get a name error or not? And what might be the cause of that error or the lack of error, respectively? Restart the kernel, run all again. Does a new error appear where it didn't before? Maybe actually keep the cells and change X to something else, and don't run it, and then rerun cell B, see if the Y value changes. Try everything, try to break things within reason in your kernel and see what happens. So here's another little kind of example. This is the amount of carbon dioxide measured in million metric tons of carbon. And our units that we care about are going to be million metric tons of carbon per year. And this is kind of, we're interested in how much CO2 is being emitted into the environment. This is obviously going to be a toy fictional slice, which we literally just produce in code here. And then we draw a graph. So this is more or less the same as before. We have a little line graph. Everything's been annotated nicely with labels and a title and a legend. So this is what we have from 2015 to 2022. This is how much CO2 is being produced per year. So pause the video. Here's our nefarious pencil. I want you to discuss, and for now in your own mind, but eventually when we meet in person, what comparisons might actually be valid given just a short series. So 6 or 7 years is maybe not sufficient time to get an abstract trend that makes sense. If you try to get an average over this, it might not tell you the full long-term story of CO2 over decades. And what might you want to add? Like what other kind of variables might exist in the environment that can tell you something about these variables? Obviously, countries with a massive population like China, India, the United States might be putting out more metric tons of carbon dioxide into the environment than smaller countries like Luxembourg or Ireland and so on, because they have more people. So individually, if you break things down on a per capita basis, what does that look like? Maybe you want to break down by sectors. So maybe one sector is producing an awful lot of CO2, but others are actually making huge improvements. And how can we measure uncertainty? So before we measured uncertainty by fluctuating standard deviation we had, like a range and a window that we've passed over our data. But are there other ways we might want to think about our uncertainty about this kind of scenario? So think about that and bring it to class. Here's some analysis habits that we want to foster throughout the whole semester. So first we want to sort of just investigate or look at the data. So you can use this using calls. You can do this by calls to df head, df info, df describe. So run all of these in the environments that we're providing. See how they differ from one another. We've already kind of done this a little bit in our examples before. So whenever we have this code, we kind of printed it up on the screen to make sure nothing weird is going on visually. This is a crude approach, but it sometimes can help find problems early. Next, try to plot some things early. I know eventually you're going to want to produce meaningful plots and the result of like model analysis, but sometimes it can help just to plot your data, do a scatter plot, do a line graph, because this can also help to catch some problems earlier. The kinds of problems you're going to encounter at this stage are something we're going to elucidate over the course of this class. And if you can only put out a certain number of rows of data using these tools before your human minds lose track of the raw numbers. So sometimes a visual representation is more attuned to how humans process information. And always, in your code, like I use df this and df1 or df2 that, but usually you want to just, like as you're probably seeing in other classes, name your variables in a way that makes sense, that carries some meaning for you. Finally, you want to make the plots explain themselves. So take an extra moment to add those X labels, Y labels, titles, legends. That's going to be a lot better for you later on when you're coming back to this. You just do a bit of extra work up front. It's going to save you a lot of extra time later. When you get stuck, you're going to produce error messages. We might see some of those in class together, but read the last 2 lines of the error message. That's normally where you start with the actual problem. You can restart the kernel. So like after you've tried to debug what the problem is, restart everything by going to the whatever. If you're using Jupyter Lab, you go to the top options bar, kernel, restart the kernel. Always check your environment like we talked about before. You make sure you're running the right environment. And if need be, search for the exact error text somewhere. So if you're going to a search tool or even increasingly large language models, don't just say, well, my code doesn't work. Like copy the actual error message as well. And if you're communicating to your human teammates or course mates, be as specific as possible. If you do ask for help, include the code cell you're running, the full error, the executable, and your operating system. I'll put a little caveat here under warning. So this kind of behavior is good in general, like if you're having trouble and you want to expose it to the broad community and you're comfortable, you're doing open source work anyway, and attribution's on an issue, like generally this is the right sequence of steps you want to take. Because this is a class, and you are being marked for things, you probably want to exercise caution before you just copy your entire assignment to our forum, obviously, right? So when in doubt, somewhere in between each of these steps, ask me. So by now you should be able to launch Jupyter Lab and run a notebook. You should be able to create and activate a particular environment, and I recommend conda as much as possible. You'll be able to verify your setup with kernel checks in that environment. You'll be able to check your library versions that you have in that environment. You'll be able to load data, inspect it, and do basic cleaning. Maybe not the cleaning right now, but copy the code from these slides and run it in your environment. And produce a plot, define that plot in a 1-sentence takeaway. And that's more or less it. So I wanted to take the time to make sure your tools are all set up. In some sense, a lot of the tools you're going to develop are mental tools, cognitive tools. But we want to make sure that we're not spending time in later weeks trying to wrestle with library versions. Get comfortable with this now. Save your time later. Be nice to your future self. Thanks so much. On to Module 3.